Okay, let's dive into the world of statistics. Now, I know that word can sound a little heavy, but stick with me because today we're going to break down the two biggest ideas in the entire field and turn what looks like just a bunch of data into actual useful knowledge.
Have you ever wondered about this? How can a drug company be sure a new medication works for millions of people when they've only tested it on, say, a few hundred? It feels like a giant leap of faith, doesn't it? Well, it turns out it's not faith at all. It's statistics. And this exact problem is what statistics was born to solve.
And at the very heart of this whole challenge is one fundamental idea: the huge difference between a population and a sample. Think of it like this. The population is everyone we're interested in, like every single person in the world with high blood pressure. That's a massive group. We could never study all of them. So what do? We grab a sample, a much smaller, manageable group that's chosen from that larger population.
And that leads us right to the core question of pretty much all of statistics. How can we use what we learned from that tiny little sample to say something true and meaningful about the entire population? Well, the answer comes in two parts, using two very different kinds of tools.
Let's start with our first tool. I like to think of this one as the magnifying glass. This is descriptive statistics.
This is all about the here and now. It's about describing what you can see right in front of you. We're not guessing, we're not predicting, we are just using numbers and charts to get a really clear, simple summary of the data we've actually collected from our sample. That's it.
To make this super concrete, let's just imagine we've gone out and measured the heights of 10 basketball players.
So here's our data, our sample. Right now, it's just a list of numbers. And honestly, it's kind of hard to make sense of, isn't it? What does this list actually tell us? We need a way to boil it down.
And boom! With one simple calculation, we have our first piece of real insight. We find the average, or the mean, and we get 1.68 meters. Instantly, that one single number gives us a mental picture, a central point for our group. We have just described our sample with a single, powerful value.
And of course, the average is just the beginning. We've got a whole toolkit here. We can find the median or the mode. We can figure out the standard deviation to see how spread out the heights are. We can make charts and tables. It's all about painting a detailed picture of the data we can see.
Okay, that's great for what we can see, but what about everything we can't see? For that, we need to put down the magnifying glass and pick up our second tool, the telescope. This is inferential statistics.
This is where we make the leap. Inferential statistics takes that sample data we've so carefully described and uses it to make an educated guess, a generalization or a prediction about the entire population. We're using what we know to say something smart about what we don't know.
So notice how the question totally changes. We're not asking about our 10 players anymore. We're asking a much, much bigger question. Are basketball players in general, as a whole population, taller than football players? To answer that, we have to infer. Let's just put this side by side to really nail it down. Descriptive statistics asks a question like, what's the average height of these 10 players? The focus is only on the data right in front of us. But inferential statistics asks, are basketball players in the population taller? See the difference? The goal is to make a huge conclusion about everyone.
Okay, let's go back to our big, high-stakes question from the beginning and see how this all works in the real world testing that new drug.
The process for doing this kind of research usually follows these 4 basic steps. Let's just quickly walk through them.
So first up, the company collects its sample data. They can't possibly test the drug on every person with high blood pressure, so they find a representative sample of 200 patients.
Next, they pull out the magnifying glass. They use descriptive statistics, and they find that on average, the patients in their study had their blood pressure drop by 15 points. This number, 15, is a descriptive statistic. It tells them exactly what happened in their specific group.
And now we get to the giant, all-important inferential question. Is that 15-point drop a real effect of the drug? Or is it possible that they just got lucky with this one group and the result was a total fluke that happened by random chance?
This is where the inferential toolkit is everything. Researchers use powerful tools. You might have heard of things like a t-test that act like a statistical referee. It basically calculates the probability that their result was just a coincidence. And if that probability is low enough, they can confidently raise their telescope and infer that yes, the drug is likely effective for the entire population.
So after all that, what's the one thing you really need to remember? Let's boil it all down.
It really comes down to this. Descriptive statistics is the magnifying glass. It helps you see all the fine details of the sample you're holding in your hand. Inferential statistics is the telescope. It lets you use that sample to look out at the whole universe, the entire population. One looks close, the other looks far.
So here's my challenge to you. The next time you see a news report or read an article with a statistic, just pause for a second and ask yourself a simple question. Is this number just describing a specific small group they looked at, or is it making a bigger leap, a claim about everyone? In other words, are you looking at a finding from a magnifying glass or from a telescope? Just knowing that difference makes you a much, much smarter reader of the world.